All right, hi everybody. Welcome back for day 2 of the Tripods i.i.d workshop on machine learning and supply chain management. We'll get started right away with our first talk. Our first speaker is Max Zhen. Hi, Max. Good to see you. Max is a vice president and pro-vice chancellor of research and the chair professor in logistics and supply chain management at the University of Hong Kong. He's on leave from UC-Berkeley to take that role. He got his PhD from the Department of Industrial Engineering and Management Sciences at Northwestern and has done lots of research in integrated supply chain design, operations management, data-driven operations, and so on. He's currently the chief supply chain scientist for JD.com, and he's the president-elect of the Operations Management Society. He's a fellow of Informs, and one other thing I'll add that he didn't put in his bio is that he's the co-author of an excellent textbook on supply chain theory, which I am the other co-author of. So with that, Max, thank you.
Hi, Larry. I suddenly feel so emotional seeing Larry after 2 years. So this is 10 p.m. in Hong Kong. I was really sleepy before the workshop, but now I see Larry, I see all the good friends, so I feel excited again. So I will continue my talk on the practical end-to-end inventory management model with deep learning. So my name is Max. I've been working at UC-Berkeley for 24 years, and now I'm at Hong Kong U. Being the vice president of research. But the more I'm on the leadership position, I feel like industrial engineering and operations management actually have a much bigger role to play. So today I plan to share with you some of my recent research with my students and my teammates from JD.com. It's really about basically some fundamental changes to our discipline. So I will go directly to the topic because I only have 30 minutes. Let me see how it works. Okay. So everybody knows that data science and AI has become a really popular topic. And I just want to broadcast that with UC Berkeley and Georgia Tech, we just have a center of AI Institute for Advances in Optimization set up with 20 million US dollars funding from ASF. But before this, we all know that MIT have a Institute for Data Systems and Society. Berkeley have a division of data science. Now actually it's a school of data science. And in China also we have Tsinghua have the AI Institute, and actually I'm Hong Kong U. I'm setting up an Institute of Data Science with a generous donation of $150 million from some alumni. So this is a popular phenomenon globally, right? You can see this from Berkeley, MIT, Georgia Tech, Tsinghua, and Hong Kong U. So what is the driving force? Because people believe that AI and machine learning can be the dominating factor in making decisions, right? So because people see in AlphaGo that the machine learning algorithm can beat any smartest person on world, right? But then, we are the decision makers, right? When we look at all this, we have a clear mind about the limitation of all this, right? In AlphaGo, if anybody play Go, there are all set of rules, constraints, objectives. You can easily program this into some optimization algorithms. But if you actually move to a real world, then the decision making becomes much more complicated, right? So the future for AI, we need less artificial but more intelligent. So there are a lot of business cases that AI cannot beat human beings. So this is where we can contribute. We can actually come up with better decision-making models to help business owners and organizations to come up with better decisions. So this is the focus of my talk. So I have given a lot of thought about this, right? So basically, if you look at the left, this is our domain, industrial engineering, or OM, or decision making, or whatever name you call it. But we try to solve many of the decision making problems. But on the other hand, we have all these machine learning algorithm experts. They claim that they can do better than us, right? So actually, in Berkeley, we even had a few candidates, job candidates, came to Berkeley, claim that we don't need to know production, location, inventory models because our machine learning model will be better than any of your algorithms. So we were, intimidated. We were frustrated, but then we eventually asked ourselves, right? Can our domain knowledge actually lead to better or faster AI solution? Right? We don't argue with machine learning or AI domain that they can come up with pretty good solutions, but can our domain knowledge help, right? And then the second question is that can actually the other way around, can machine learning and AI help us solve our decision problem better, right? For many of our NP hard problems, TSP problem, for example, can some of the machine learning AI algorithm help us solve the problem better, right? So those are the two fundamental problems that make us think whether how our discipline should evolve, right? Should we work with machine learning? Because there are a lot of departments actually basically give up. They don't want to hire anybody working traditional i.i.d. or OM. They just want to hire anybody with a machine learning title. But on the other hand, there are many traditional i.i.d. department or OM department still want to hire traditional i.i.d. or OM. So what is the right way to go? Actually, I don't really have a good solution, but I want to give you a couple of examples from my own research. Hopefully this will shed some light on those two questions. So basically, we have three options. Either we surrender, right? So we basically give up. We say, okay, i.e. is basically a dying field. We cannot compete with machine learning. So we should hire all the people from computer science, machine learning. They will teach us how to do decision making better. The other option that we will hide, we try to pick out, we try to see whether there's anything we can grab or we can learn, and then maybe we can help us make better decisions, right? The other option that maybe we should work with them, right? Maybe we can work with machine learning expert or AI expert, and then maybe with this joint force, we can make AI better, we can make i.i.d. better, right? So if you look at all these business analytics program, if you look at the core curriculum, you will see that there will be optimization in it, there will be statistics in it. So maybe there's some hope that we can actually help them make better decisions, right? So this is kind of the theme of my talk, is that can we actually, being a data-driven decision making person, can we make better decisions with machine learning techniques? So this is the traditional optimization problem we try to solve, right? So this is just a problem from one of my paper. We try to come up with an optimization model. We try to minimize or maximize some objective subject to some constraints. But in the traditional setting, we normally would assume that all these parameters are given, right? Or in the stochastic programming setting, that even though the parameters are not given, but we know the distribution of it. So we make a lot of assumptions. But then this is proven to be less useful in practice because when I work with many companies, from Amazon to JD.com, they will tell me that if I know the demand distribution, I don't need you anymore. Right? That's kind of true because if they know the demand distribution, they can come up with very, very good solutions, right? In Wall Street, right, there are a lot of double PhD holders, right? They have a PhD from physics or mathematics. They don't have to know simplex, but they can solve optimization problem better than us, right? So this is our limitation. If we have to assume we know all these parameters, then we cannot work with the industry, because for industry people, many of these assumptions will not hold. So we try to move toward the data-driven decision-making process that we would look at the data, we try to look at the distribution of the data, then we will claim that the demand during the next few periods will follow some kind of distribution. And then if we are not sure about this, we will come up with a robust optimization framework that we are not sure about the distribution, but it follows a family of robust distribution, right? Then we try to come up with solution. We will validate all these assumptions and solutions. So in a paper that will be published in Management Science or OR, the whole paper is maybe 32 pages, but the first 15 to 18 pages will be all the justification of the assumptions, why we use this distribution, why all this assumption makes sense. This is us, right? We try to basically justify that all these assumptions we make are useful. But can we do something different, right? So this is a research I started with GD.com. So I will talk about GD.com later, but I have 2 papers on this topic, which is inventory management, because everybody knows inventory management really well. But from the textbook we learned, with a very good textbook, Larry and I co-authored, we have all these assumptions, we have all these models about QR policy and assets policy. But when you actually work with the industry, sometimes it works, I have to say. But sometimes they will tell you that, look, your assumption of the demand or some parameters just does not hold, right? So this is particularly true with some e-platform companies. So I will share with you my experience, and then I will show you how we solve these inventory problems. So I have 30 minutes, so I will spend 5 minutes on the motivation. I'll talk about what is end-to-end, and then I will show you how we use this philosophy of end-to-end to solve practical inventory problems. And then I will show you why this model is popular in GD.com and why people appreciate our contributions. So for those of you who don't really know GD.com, it's the largest retailer in China. It's the 3rd largest internet company globally. And they have, this number is updated, they have 530 million active customers already. What's unique about GD.com is that they promise to deliver 90% of the orders within 24 hours, right? So this is really hard to imagine if you live in America, because normally if you order for Amazon, if it can deliver to you in 3 days, that's already pretty good. But their promise is to deliver 90% of the orders within 24 hours. Normally, if you live in a big city like Beijing or Shanghai, if you order in the morning, you get it in the afternoon, right? So this is what JD and Alibaba has been doing. So they have a pretty extensive network of warehouses, distributors, and then the reason that they can deliver very fast to you is that because they have about 600 warehouses in China, so that whenever you order something, they have the inventory close to you, and they can ship from the closest warehouse to you within 24 hours. But one of the challenges is that JD actually provides millions of SKUs, actually hundreds of millions of SKUs. So how do you make sure that 90% of the orders can be delivered within 24 hours? Now, this is easy for 1 SKU, 2 SKU, maybe a million SKU, but for a few hundreds of millions of SKUs, this is not easy to do. So how did JD do this? So JD, if you think about it, it is actually a combination of Amazon plus UPS, because they do have the online platform like Amazon, but they also have their own logistic firm like UPS, which can deliver the product to you. So, for people who work in supply chain design, you all know that It's all about location, location, location. So when I work with my first research project was to decide the location of the 500 warehouses. But then after you decide that, it's all about inventory, because they have to make sure they have enough inventory to deliver to you within 24 hours for hundreds of millions of SKUs. So this sounds like a very easy problem, because everybody who have gone through i.i.d. or OM training, you will know this inventory management is a simple problem. It's a basic trade-off between the overstock and understock, right? So if you observe the inventory trajectory, you'll see that at a certain time you have to produce the order, then the inventory level goes up, and then the demand comes, and then it drop to a certain point you order, but there's a lead time, right? So after a certain lead time, you get your inventory, but then demands keep on coming, and your inventory level will go down. So the key question is basically when to place the order and how much to order, right? If you order too much, then there will be extra inventory here. But if you order too little, then you will run out of inventory before the reorder time. So the key question is that how much should one order at a certain time? So if you know everything, if you know the demand parameter, if you know the distribution, you know the order cost, then you would know that if there's no fixed cost, then basically you can try the optimal policy, the base stock policy, right? But this is really built upon the assumption that you know the demand distribution, you know the parameters. But for e-commerce platform, to know exactly the unit cost of a particular SKU is not easy. Because even though you know the ordering cost, but the ordering cost is for maybe 300 units together, right? Then the 300 units go to different warehouses, go through different transportation routes. So the cost associated with each particular unit of that SKU is very different. So it's not you can't even easily assume that you know the ordering cost of every SKU. On top of that, if this is a typical demand distribution of a product on JD.com, because in China, normally they will have a lot of promotion, right? This is one of the holidays that the demand will goes up really, really high, and then those are some other holidays during summer. So if you assume the demand is i.i.d. normal distributed, then you are very wrong, right? So with this kind of demand distribution, we cannot easily apply the optimal policies we learned from the textbook Larry wrote. So what do we do? Normally, the focus for every industry is to do a better demand forecasting, right? So, they will look at all these different, with machine learning even, they will look at all these different features like inventory level, historical sales, lead time, item information, vendor information, warehouse information. They will do a great forecast. And then based on the forecast, they try to do a better inventory planning. And this is why LlamaSoft was bought by Coupa Software at $1.5 billion US, because he has been the leading provider for a lot of modules we talk about, demand forecasting, location models, inventory planning, right? But I actually think there's some fundamental problem with this approach. Because if you do forecasting and then do inventory planning, there will be error accumulation because first of all, the uncertain sources, VLT, when the lead time and demand, all this uncertainty will accumulate, and then eventually, just like bullwhip, your error will become bigger and bigger. And then the forecasting goal doesn't match the optimization goal, because in forecasting, you try to minimize the MAP, but in optimization, you try to minimize the holding cost. So these objectives are not in line with each other. So because of these fundamental problems, we try to avoid this two-stage framework. We try to come up with an end-to-end one-stage decision making for inventory planning. On top of this, actually for JD.com or Amazon, the inventory planning problem is much more difficult. As I mentioned, there are hundreds of millions of different SKUs, right? There are different products, right? Some of them are long tail products. You can sell easily sell many of them because unless you have a promotion or a holiday season, people don't buy this product very often. And then there are some fast-going products that you put there, you can easily go. So the inventory planning will be quite different for these two different categories. And then there are many products that are sensitive to promotion, right? Whenever you have a promotion, the demand pick up very quickly. But if you don't have any promotion, the demand will be really flat. So, how do you manage all these different products? In JD.com, actually, when I talk to the business people, they tell me that for a good business person, if he or she can manage 200 SKUs perfectly, meaning that you manage the demand forecasting and inventory and transportation planning for 200 SKUs, that's already quite a bit. But if you have hundreds of millions of different SKUs, how many people you need to hire? So this is certainly not a sustainable solution because you cannot hire that many people. So they certainly need an automatic inventory planning framework so that they can use AI to do the inventory planning. So this is why they work with us, try to ask us to come up with an AI solution so that they can order inventory for hundreds of millions of different products without all the salesperson spending all their time and energy on all the SKUs. So what we try to do is that we try to apply the end-to-end framework. As I mentioned earlier, in the earlier two-stage framework, we look at all the features, we do a good forecasting, and then we do inventory planning. But what we try to do is that we try to get rid of the stage. We will not do a lot of forecasting. We try to go directly from the features of the inputs and go directly to the inventory planning stage. So basically, our goal is to look at all the features and then come up with an optimal order quantity. Look at the time, make sure I don't. Okay, I only have 4 minutes. Okay, so basically we propose a end-to-end framework with supervised learning. Basically we try to achieve that we will learn all the information from the features from the data, and we will go directly to the inventory decision making. So for this supervised machine learning, we all know that we have a lot of input features, right? So there are two major training sessions. First, we need to come up with a training data set. Basically, we need to look at the feature, and then with this kind of feature, we need to come up with the right answer, right? Based on the feature xi, what is the right decision, yi, right? This is the training part. The second part is that how do we actually come up with the F function, right? How do we come up with a powerful model to fit the complex relationship between the features and the decisions? So for the training part, this is how IUR can contribute, meaning that with all these XI features, actually we can be better than the machine learning people to come up with the training set, right? Because we know how to manage inventory better, right? So with all the features of XI, right, all these different features, the question is that what is the target YI, which is the right answer for the reorder problem? How much inventory we should reorder? Right, this is the problem we have learned from the textbook Larry and I wrote, right? Based on all these features, we need to decide order quantity. So I don't have much time, but I just want to tell you that without our domain knowledge, machine learning people would look at all the different options. They try to simulate, they try to look at all the options. It will take them a long time to come up with the optimal YI. But for us, actually, we know how to solve this problem. It's a DP problem, right? If you look at this DP problem, right, we try to minimize the inventory holding and ordering cost, right? This is the cost. Then we can optimize the AI, which is order quantity. And then actually for our problem, we can actually come up with a closed form solution. So that way we can train the machine learning algorithm much faster than machine learning algorithm, because for computer scientists, they don't know all this DP formula. They don't know how to solve yi optimally. And here we actually have a closed form solution. We can have a really fast and optimal training for the yi. So this is the first part, right? With our inventory models, we can actually have a training data set much efficient than machine learning scientist. The next question is that how do we build up a powerful model to fit the relationship between features and decisions? So with this, we need to rely on a recurrent neural network. I don't have time to go through the detail, but we use a quantile information for this neural network. And then for the network, we actually will spin out the demand forecasting and also the inventory ordering decisions. So we came up with basically a multi-period inventory problem with the machine learning framework. Our main contribution is that we can actually come up with a labeling method using our optimal inventory policies to generate the training data set much more efficient than a typical computer scientist. And then we also came up with an innovative design of deep neural network so that we can easily learn with many features and then come up with a very good decision problem solution for the inventory management. So just a quick wrap up. So we have worked with JD.com. We did a lot of experiment. We first did an offline experiment. We tried the predict and optimize framework with the same neural network, and then we try our end-to-end method. And we showed the benefit of our method. And they agreed to let us go online. So when we went online, we actually tried on 9,000 different SKUs. We compared with their original method. We showed a significant benefit of our method. Actually, we reduced all the metrics, for example, holding cost, stockout cost, and then all these measurements are improved by at least 40%. And then they are in production of our algorithms. So they are now working with more than 12,000 different SKUs. And then they try to actually expand this. We are shortlisted for Gartner Power of the Profession Supply Chain Award. We are one of the top 6 finalists for this award, and we try to actually move on to the final 3 and the final one. So, Larry, did I run out of time?
You ran out of time, but
sorry.
if you, that's okay. If it's okay with everyone, we can take a few minutes for questions and then move on to our next talk.
Okay.
Max?
Fine.
Okay, thank you.
Sure.
All right, anybody have questions? Jan.
Wonderful talk, Max. Thank you. I had a question about using the closed form solutions of the order up to model and how you use that for supervised data pairs. I believe that's what it is about.
Right, exactly, yeah.
We'll take this.
So without our closed form formula, machine learning expert will try all different combinations. We try to solve all the different points. For us, we don't need to try different millions of options. We go directly to the optimal one because we know, given the demand distribution and all the parameters, we know the optimal one. So we can train the data set much faster than a computer scientist.
That's a very cool idea. Thank you.
Thank you. Thank you.
Was there one other question, Andrea? Thank you.
So the nice talk, I really enjoyed it. So one question is, Is it really like a very constrained optimization problem at the very end or not?
That's a good point. For constraint optimization, it will be much more complex.
Yeah.
So for this setting, I didn't have time to go to the second phase. My second phase of the talk is that we look at the setup cost. We look at more constraints. It becomes much more complex. But I only have half an hour, so I didn't go to that part. but I fully agree with you that with constraints, with more limitations, our method will get also more limitation. But I still believe that we can have an advantage over computer scientists, because if I look at the 3 QA question, we have a question and then somebody have a question that why machine learning couldn't get closed form, because actually with the setup, we actually can solve the problem much better. I have another paper on the delivery problem. Actually, it's a traveling salesman problem. And because we know how to solve traveling salesman problem, we actually came up with a feature that computer scientists cannot come up with. So we can solve the problem much more efficient.
Well,
this is
the domain knowledge, right? I mean,
yeah, exactly. So I strongly believe that if we know some domain knowledge, we can actually be better than the machine learning expert. We can apply this and we can train our model much more efficient.
Thank you, Max.
Thank you. Sorry, I'm over time.
I know we have some more questions, but we'll keep it moving, and maybe
Right.
Max, maybe you can email Max.
Okay.
Thank you.